Let's look at the next application of the differential equation concept. And in this context, we'll be looking at the application of the idea of first order differential equations to electrical circuit. And the circuit we'll be using in this particular context would be an AC circuit. That's what there, an alternating current circuit, right? I'm not doing physics here, but then just a brief. An AC circuit is a circuit in which current flows in one direction and then in the reverse direction. That's what they taught me in year one. I still remember up to today. One of the major distinctions between an AC circuit and a DC circuit has to be with the presence of what there? The inductor. There are three key components of an AC circuit: the resistor, the inductor, and what again there? The capacitor. The resistor offers resistance, which is what there? An opposition to the flow of electrical current in a circuit. The capacitor is used to store charges, and the inductor is used to store electrical energy in a magnetic field when current is passing through them. Now, in this context, in your first year, year one, if you go to physics, what we did, electromagnetism, waves, and optics, we saw the combination of these stuffs. When you looked at an AC circuit containing resistor only, inductor only, and then capacitor only. We also saw them in combination. That's ROC circuit. An ROC circuit is simply a circuit that has what there? Just resistor and what there? Capacitor as the main thing there. An RL circuit is a circuit that has what there? Resistor and what there? Inductor. Then we now look at three of them combined. That gives you what there? RLC circuit that has resistor, inductor, and capacitor. All combined in what there? Series. Emphasis on series arrangement. That becomes what there? End-to-end arrangement. Now, in this context, for first order will be used to solve RL, capacitor, inductor, and then RC, RL, resistor, inductor. So look at two things here: RL circuit, resistor, inductor circuit, and then RC circuit, resistor, capacitor circuit. Look at two of them. Then the RLC would need second order differential equation. All right, so let's take them. Take that, please. For this, take down, please. Here, okay, recall that, take down. Recall that there are three major components of an AC circuit. The first one there is resistor. Let's call this an R. The second one is inductor. Inductor is L. Number three, we have capacitor. That's C. All right, that's the first thing I want to note. We have this. Resistor is used to measure resistance in ohms. Inductor is used to measure inductance in what? In Henry. Inductance is in Henry. The symbol for this is omega. Henry is H. And then capacitor is what there? Farad. Capacitance in farad, F. Right? This is used to, resistor is used to oppose the flow of current in a circuit. Unit is ohms, here's the symbol. Inductor is used to store electrical energy, right, in a magnetic field when current passes through it. The SI unit is in Henry, abbreviated H. And finally, you have capacitor. Capacitor is used to store charges, electrical charges. The unit is farad. Your symbol is F. All right, let's take them. So we'll look at this in two concepts. The first one will be an RL series circuit. RL series circuit, please. Let's start with this. By the way, okay, just for space sake, let me do it here. What's the circuit symbol for resistor? Hmm? There are two circuit symbols for resistor. There are two circuit symbols for resistor. The first one is this one here, the zigzag. The second one is this, just this. Yeah, there are two. When you now have this, what's this called? That's a variable resistor, also called what there? Rheostat. We don't do physics now, right? Not doing physics. Okay. Somebody was asking me the other day, how do you know how do you know all of them? How do you know? I'm like, everything is connected. Science is connected. That's why they say science is a body of knowledge. How do you know physics? I don't know. It's weird that you know physics, you don't know chemistry. Come on, the same thing now. You don't know organic chemistry, but you know physics. Come on, they're the same thing. Everything is connected. Organic chemistry, biology, everything is connected. So if you know math, you should know physics, chemistry, biology, everything is connected. For your inductor, what's the symbol? Yeah, yeah, that's it. Science is connected. The question is, do you see the similarity? That becomes the question. Sorry? Then, yes, there's this thing we did here. This thing we just did here in decay population. You're mentioning what the bacteria. Did you observe it? Yes, now bacteria growth. Yes, you observe it. All right, take down, please. Consider an electrical circuit of resistance R in ohms. It's actually what? The fact that you're always smiling when you're saying this thing. I was telling you, why is it always, why do you always smile like, what's the funny exactly? I don't know. Why do you always smile like that? This is not a physics class, so don't stress. Just don't stress it. All right. Consider consider an electrical circuit of resistance R in ohms. R in ohms and inductance L in Henry. I've already said that already. Connected in series as shown below. So you have this. Connected in series as shown below. You have this. Where the battery or generator, where the battery or generator produces a voltage, where the battery or generator produces a voltage in volts, produces a voltage V in volts. What the battery or generator produces a voltage V in volts and a current I in amperes. And a current I in amperes. At any time t, called small t, and a current I in amperes at at any time t, small t. Consider the relationship below. Consider the relationship below. Now let's start with current. What's current? What's electrical current? How do you define it? How do you define electrical charge? How do you define current? What? Yes. So current is simply what there? The flow of electrical charges. That's one concept. We could still look at current as what there? The the rate of change of what? Electrical charges. If electrical charges is flowing for any time, that means charge over what there? Time. That's the first thing there. So the first thing you want to note is that recall that electrical current I is the rate of change of charge per any time, or flow of charge per any time. That's what you want to consider. So current it's equal to charge over time. What's Q from here? From here, we can say that Q. Okay, fine. Let me cross. Is that important? Okay, let me cross multiply. This times this, you have the word there. The Q is equal to what there? I the T. Integrate this cancels this. So it means that charge Q is equal to the integral of I dt. Keep it pending. Q is equal to the integral of I dt. Keep it pending. Let's look at something. So the charge is equal to the integral of current dt, or we get current by differentiating charge with respect to time. That's it. The big part, from Ohm's law, what is voltage across resistor? From Ohm's law, voltage across resistor V is equal to what there? IR, right? Or let's just say RI, same thing. IR or RI, same thing. That's resistance times current. We have that. Voltage, let's look at voltage across inductance or inductor. The voltage across inductor, let's call this VR. We call it VR. Voltage across resistor, VR. Voltage across inductor, VL. VL is equal to I dt. So for an inductor, the voltage across the inductor is simply equal to the product of the inductance and the rate at which current is flowing, basically. But this is actually under electrical. All right, so we have this. Voltage across resistor, VR, is RI. That's from Ohm's law. Then this one, so you can check this. The voltage across an inductor is simply equal to the product of the inductance of the inductor and the rate at which current is flowing through the inductor. So you have L dot di dt. This. Now proceed. Take that, please. From the above, take a paragraph. From the above, we can formulate a first order. From the above, we can formulate a first order. Non-homogeneous ordinary differential equation. From the above, we can formulate a first order non-homogeneous ordinary differential equation using using this. How do you pronounce this? What's this? Kirchhoff. Kirchhoff. It's not called Kirchhoff. It's called Kirchhoff's. Quite pronunciation. So this is pronounced Kirchhoff. It's not an English word. It's not Kirchhoff. It's not Kirchhoff. It's called Kirchhoff. I remember when I was learning this, I'm very intentional about pronunciation. So I have to go and check it online. And obviously, it's called Kirchhoff's law, not Kirchhoff. Using Kirchhoff's voltage and current laws. We use Kirchhoff's voltage law to get the first order application for RL series. Then we use Kirchhoff's current to get for RC. Yes. Let's proceed, please. Using Kirchhoff's voltage and current laws. Let's look at the voltage law. Kirchhoff's voltage law. This is just a summary. Kirchhoff's voltage law states that the algebraic sum of the voltage drop, the algebraic sum of the voltage drop, the algebraic sum of the voltage drop around any closed circuit, algebraic sum of the voltage drop around any closed circuit is equal to the resultant electromotive force in brackets E, capital E, this one here. The resultant electromotive force, that's E, in the circuit. In the circuit. So look up, please. We're saying that the sum of the voltage drop in a circuit is simply equal to what there? The electromotive force. That is a way of defining Kirchhoff's voltage law. Having said that, considering the elements in this particular concept, which is R and L, we'll get the voltage drop in the resistor as well as the voltage drop in the inductor. These are the two elements here. And we'll simply equate to what there? The electromotive force. For the resistor, what do you have? Ri. For the inductor, what do you have there? This. So the voltage drop in this circuit, that's for the inductor, which is given by this L, the I, the T, plus the voltage drop for the resistor, which is Ri, is equal to what there? The electromotive force. You have E. So you have this. Now if you look at this, this looks like a first order non-homogeneous differential equation. dy dx, y, then your constant as may be. What's my first task here? When we're doing first order non-homogeneous, my first task was to make sure that the dy dx was a constant, what's it called? Unity. That means its coefficient should be what there? 1. So from here, to make this 1, I'll divide here by L, divide here by L, divide here by L. I'll be left with what there? di dt plus the variable here is now I. So what's my constant here? R over L. R over L into I. It's equal to what there? E all over L. I now have a first order non-homogeneous ordinary differential equation in terms of what there? I, the current. So, so please note this thing, note that the relation between current and what charge is that current is equal to what there, charge per unit what there, time. All right, let's solve this. How do we solve this? What do you do? Your first task to find what there? The integrating factor. What we said, integrating factor IF is equal to exponential integral of, we said u of x. What is u of x? U of x is whatever thing that's attached to what there? Y in that concept. In this case is I. So u of x becomes what there? This one here. R over L. That's R all over L with respect to what there? The t. So integrate this with respect to what there? The t. All right, let's integrate this. What do you get here? How do you integrate this? What do you do? This will be equal to, in integrating or integration generally, we said the constant goes outside integral sign. The constant here is what there? R over L, integral of what there? The t. This is a constant. It doesn't have t. So take it outside integral sign, then put the t. We've said this countless times. Integral and d, what happens there? They cancel out. So this will cancel this. I have that the integrating factor IF is equal to exponential R over L times what there? T. This is my integrating factor. What's my next task there? Use integrating factor to do what there? Multiply through. Multiply through by integrating factor. That's how we solve this. We multiply through by IF. Please, if you missed out our last class on integrating factor or on how to solve first order non-homogeneous ordinary differential equation, right? Go check out that video. See how we solve things of this nature. We are here. Let's multiply through. So it's simply this one here. Exponential R over LT multiplying all of this. That's what's there. The I, the T plus R over L I is equal to what there? E over L. You have this. Alright, so expand this, what do you have here? This and this, what do you have here? Exponential R over L times T into what there? The I, the T. Take this and this, what do you have there? Plus R over L exponential R over L times T into what there? I, yeah? Is it correct? Yes. Or should we invert them? Same thing, all right? So it's equal to this and this. So E over L exponential R over L T. So we have this. All right, that's on expansion. And we know the idea behind this. We said this can be expressed as what there? D all over what there? The T of what and what there? This one here, this one. Which is what there? I times what there? The integrating factor. What's the integrating factor there? R exponential, please. Exponential R over L T. You have this. It's equal to your answer. E all over L exponential R over L T. So we have this. Let's solve this. How do you solve this? The T goes this way. So I have D of I dot exponential R over L t is equal to, dt comes this way, I have e all over L exponential r over lt dot dt. So I have this. Next step now be integrating. So integrating through. If I integrate through, what do I have there? The integral of d I dot exponential r over lt. This is equal to the integral of e all over L exponential r over lt dot dt. So you have just integrate both. If you're true, you have this. All right. So how does this work? We know first things first that integral cancels what there? Differential. So I'm left with this. I'm left with I dot exponential r over L t is equal to, when it comes to integrating this, the concept here is that the constant goes outside the integral sign. That's e over L is going outside. So I have what there? E all over L integral of what there? Exponential r over L t dot dt. From here, I have that I dot exponential r over lt is equal to, this gives you e all over L. How do you integrate exponential term? What do you do? Differentiate the power and take it as what there? Denominator. What's the power here? The power here is r over lt. Now, question. If I have 2x, if I differentiate 2x with respect to x, what do I get? 2. In essence, whenever you have, so what if I have 2t? Differentiate 2t with respect to t, what do you get there? 2. So what if I now have r over lt? Differentiate this with respect to t, what do you get there? R over L. That's it. So when it comes to integrating this concept, the idea is simple. I will differentiate this, the power, I will take as what there? Denominator. In essence, this man looks like this, exponential r over lt all over this one here, r over L. Right. Let me put this as what there? A square bracket. So you have this. This is this plus what there? C, your constant of integration. Looks very interesting, right? Yeah. This is what they call mass, not those 2x plus 3 is equal to this. Find the binomial expansion. Are you playing? Those are BB mass. That's what they call maths. To deal with this stuff, let's see. All right. So how do we solve this? What do we do here? This is basically, watch this please, watch this. This is basically I dot exponential r over L t. It's equal to, how do you simplify this? So here's the thing. If I have A all over B over C, for instance, this is simply A divided by B over C, which can be written as what's there? A divided by B over C. This becomes what there? A times what there? C over B. The idea is this: if something is dividing a fraction, all you have to do is to take the inverse and multiply it. That's the concept. That means I'll now be having E over L. To solve this one here, it's as easy as take the inverse of this, turn it upside down, it becomes what there? L over R. Use it to multiply what you have there. That's exponential R over L t this plus C. So what do you see there now? This will cancel this, it's off. This now becomes what there? I into exponential R over LT is equal to, what do I have here? E over R. That's what I have here. The L's cancel out. Having E over R, that becomes equal to E all over R exponential what there? R all over LT plus what there? C. I have that, right? So I have E over R, this plus C. My next task will be divide both sides by what there? This. Right, divide by this. Just copy that, let's proceed. Just hopefully you copy it correctly. At this point, divide by exponential R over LT. That becomes I dot exponential R over LT all over exponential R over LT. This is equal to this one here, E over R exponential R over LT divide by exponential R over LT plus C all over exponential R over LT. Right, so how does this look? How does this look? Looks good, right? You're not feeling like what? Newton or Einstein, which of them? Or Galileo Galilei, which of them? And this is what they call mass, not all those 2x plus 5, right? Binomial expansion. This one, see mass here, see mass, very nice. All right, let's proceed. Please go and learn how to derive, to build your muscle. Learn how to derive. From here, this cancels this. You have that I is equal to, please watch this, I is equal to this. We'll cancel this too. It's off. What do you have there? E all over R plus C all over exponential R over LT. Please look up, please. Let me write this in index form. Please. This in index form, I would have, watch this please, I'll have something like this. Look up, please. I'll have something like this. I'll have that I is equal to E all over R plus this in index form becomes C. This one here, if I remove C here, what do you have there? 1. 1 all over this in index form, what do you have there? Exponential minus R over LT. Right. So you have this. So comrades, we've now reached the first part of the equation. We'll call this equation 1. Now reach the first part of the equation. Call it equation 1. Let's proceed. I'm trying to derive an equation for something. At this point, if you look at what they said in the note there, they mentioned something called what there? A closed circuit. Before the closure of the circuit, of course, when the circuit is now closed, current can move around the circuit. Now, at the initial stage, before the current was closed, what happened? No current was moving. It was an open circuit. So no current was moving. Before, listen, I want to explain something. Before the circuit was, they mentioned closed circuit there. When a circuit is closed, it means current can flow through it. Now, before the circuit was closed, it was an open circuit. That means at the initial point, what happens there? The circuit was an open circuit, which means that what there? Current was what there? Zero. No current was flowing. That means at initials, open circuit, we had that the current was zero. What was the time then? We had not started reading time. So time is zero, current is zero. What have we got? We have that I, 0, is equal to E over R plus C exponential negative R over L times T. What's T there? 0. Put I as 0, put T as 0. What do you come up with? Please look at this, please. From here, 0 times anything, whether positive or negative, gives you what there? 0. So this becomes exponential 0. Exponential 0 is what there? 1. So I have that 0 is equal to E over R plus C times what there? 1. And that would give you 0 being equal to E over R plus C times 1 is what there? C. What's C here? Move this over here. You have minus E over R is equal to what there? C. That's the value of C. Let's put C, which we said is equal to minus E over R into equation 1. Into equation 1. What do you get there? We have that I will be equal to E over R, E all over R plus C. What's it there? Minus E over R. So plus minus E over R C into what there? Exponential minus R over L what there? T. So I is equal to E over R plus minus this and this E over R exponential minus R over L T. We have this. Any factorizable here? Yes. What can factorize here? E over R can factorize. All right. So if I factorize E over R, what do you have there? I is equal to, bring out E over R here. What I left is there? 1. Becomes E over R. I'm left with 1 minus, take out E over R here. What do you have there? Exponential minus R over L T. This is the equation we're looking for. So the equation to calculate current in an RL circuit is given by I equal to E over R into 1 minus exponential minus R over L T. So you have this one. Please copy that. Let's proceed. Please copy that. Let's proceed, please.
Get more by joining our Differential Equations channel membership or visit www.joniemanual.com/courses and get the Differential Equations Made Easy course. Both links in video description. Get more by joining our Differential Equations channel membership or visit www.joniemanual.com/courses and get the Differential Equations Made Easy course. Both links in video description.